Now, I misspoke a minute ago. I said that this was the concentration of the tank. This isn't the concentration of the tank. This is the number of, the amount of salt, pounds of salt. Oh, there's a bad marker there. Pounds of salt in tank, okay? So, what we have here is the input in, that is the number of pounds per gallon that's coming in. And if we look at, you know, we're talking about the total number of pounds. So this equation right here, dx dt, would be the pounds per minute. That's what the change in salt with respect to time. We'd have pounds on the top, minutes on the bottom. So this input that's over here would be 2 pounds per gallon. Well, that wouldn't be in pounds per minute. We would also need to multiply here by the number of gallons per minute. Whatever that number is, okay? And over here, 4 pounds per gallon, that is, again, the output right here, 4 pounds per gallon, but we need to multiply by the number of gallons per minute in order to get this into units that are correct in pounds per minute, okay? So, basically, this K that is out here is the fraction that tells us what portion of the tank is pouring out over the case of a minute or whatever. And the input isn't just the number of pounds per gallon, it's the number of pounds per gallon times the number of gallons per minute, so we know how much salt is coming in per minute in order to get our units right. Okay, so if we look at a case where the input concentration doesn't equal the output concentration, we said right here, input and output, if they're the same, everything just stays at 4 pounds per gallon. But we're going to change that, and we're going to say 2 pounds per gallon, okay, for the input concentration. Okay, so it's going to decrease. Let's say that we've got a 100-gallon tank here. Now, why is that important? Well, in order for me to know the concentration here, if what I know is the number of pounds of salt that I have total in the tank, then I can say, well, if I know there's 12 pounds of salt in the tank and it's 100 gallons, then I have 12 pounds per 100 gallons would be 0.12 pounds per gallon. So in order to know the concentration, the size of the tank is important here. So I've got a 100-gallon tank, and let's start by saying, instead of 4 gallons here, I want to redo some numbers. Okay, so we're going to get rid of our starting numbers we had there. And I'll get rid of that too. Okay, so let's say we have 100-gallon tanks, and we start with 50 pounds in the tank. 50 pounds, that's X, okay? You know, that's where we get X from. 50 pounds in a 100-gallon tank, that is 50 pounds per 100 gallons, which is 1/2 of a pound per gallon. So that's how much salt is in the tank, all right? 50 pounds in a 100-gallon tank. Now, let's say that in addition to that, we also have what's running into the tank. And what's running in is we have 2 gallons in per minute. 2 gallons per minute. And each gallon has 3 pounds of salt. Now if we look at that, and again we want to get it in the right units here so that we can set up a differential equation. Well, we multiply those together units wise, that becomes 6 pounds per minute. That's how much salt's running in. It's liquid. We're not just running salt in. It's a you know a concentration of the water that's coming in, the salt water that's coming in there. But it's in pounds per minute, which is the right units for us to be able to set up this type of equation. So in our case here, the input coming in, 6 pounds per minute. Now, what about the output? Well, we said that we're running 2 gallons in per minute. If we're going to maintain the level in this tank, that means we're also running 2 gallons out per minute. All right, so we got to run 2 gallons per minute out. So that is this K comes from that 2 gallons. Well, 2 gallons out of how much? Out of 100 gallons. And so that 2 gallons out of 100 is 2 over 100 gallons. Okay? That's the portion that's going out in gallons per minute. And then what we need beyond that is the number of pounds per gallon. But that number of pounds per gallon, initially we know what it is, half a pound per gallon. So we know that the concentration is going to go up as we pump this in because this is 3 pounds per gallon. But that's the initial concentration. And right off at the beginning, the output would be half a pound per gallon. But as time goes on, that's a moving target, right? Because this is going to go from half a pound per gallon, and at some point it's going to be up to 3 pounds per gallon as this liquid comes in. And so this concentration level is going to change. So what is exiting in terms of an output is not a constant. What's exiting is X of T, okay? Where X is the concentration of, or the amount of salt of whatever exits. Now, we have to be a little bit careful here because this 2/100, that is in gallons per minute. No, pounds per gallon, sorry. Pounds per gallon, okay? And in order to get units that are pounds per minute, we need to know how many gallons are going in per minute, right? And since we said there's 2 gallons per minute coming in, that's this part right here, and 2 gallons out of the 100 is making this fraction, but the fraction is then 2 gallons per minute divided by gallons, number of gallons, so that's 2 per minute, and this is the number of pounds, so that product there gives me the number of pounds per minute, which then puts us in the right units. So now that's the equation that we have. Now, once we have that equation, what is it we're going to do with that equation? Well, we look at that and we say, do we have a technique to solve this equation? I'm going to get rid of the units because I'm happy with the units that I have now. And I'm just going to rewrite this over here. dx dt equals 6 minus x over 50. That's really all we have there. I've simplified a fraction, gotten rid of the units, etc. And you know, I didn't put it so that I show that x is a function of t. We're already just kind of assuming that. Now, that's an equation that we know how to solve. That's an equation where we might need to get an integrating factor, whatever else. We can rearrange this. And we say, well, then what is this? This is dx dt plus x over 50 equals 6. And when we have an equation of that type, what we do is we get an integrating factor. And the integrating factor is based on that x over 50, right? If you remember when we did integrating factors before, and I know it's been a long time, but back in section 2.1 or 2.2, we talked about this and we said, well, what we need is we need to get an integrating factor that comes from being e to the integral of this fraction. This is whatever a of x is, where a of x is the thing that's multiplied by x, okay? It's a of t in this case, I'm sorry. And so the integral of a of t dt is our integrating factor. And in our particular case here, that's just e to the integral of dt over 50. So that appears to be, I integrate that, I get e to the t over 50. That's our integrating factor. It's one of those cases where I put off partially videotaping these things for differential equations because I know I'm not going to have close enough board space. So I just want to go back over everything that's on here just quickly, okay, not everything, but before I erase it. This right here, typically when we were talking back in the section where we talked about solving with integrating factors, we would have been saying dy dx. And we would have said, and over here we have something that is a function of x multiplied by y. And then over here, some cases we had 0, those were the easiest ones. In some cases we had something else. It could be a function over here of x, but that would include 0, or include 0, it would also include, you know, constants, etc. But the key was if we had this third term, if we had just 2 terms, we could separate it. If we had the third term and it was multiplied by y, this is the technique we did in order to get the integrating factor. We would have done e to the integral of a dx, but because we're in dx dt here, we flipped the variables here, we're getting t. So we have an e to the t over 50. That's our integrating factor. And I'm sadly going to erase all this because I'm going to want to refer back to it in later pictures, but I simply don't have the board space. So, x prime plus x over 50 equals 6 was the equation we started with, multiply, based on the integrating factor, e to the t over 50. And so we have x prime e to the t over 50. I don't know why I wrote that as x prime. dx dt e to the t over 50 plus x e to the t over 50 over 50 equals 6 e to the t. Say 6, write down e. 6 times e to the t over 50. And we're going to want to solve that problem. And how do we solve that? Well, again, harkening back to what we had done previously. The reason we did this was because we could look at this and say, that came from having a product. What was that product? That product was x over 50 times e to the t over 50, right? If you start with x e to the t over 50, and assume that x is a function of t, okay, which we are for this whole problem, okay? Hold the first, take the derivative of the second. What will you get? Well, you'll have the x, which is held, and the derivative of the second will give you e to the t over 50, and then 1 over 50, which is where this term comes from. Then hold the second, take the derivative of the first, there's holding the second, derivative of the first is just dx dt. So that left-hand side is just the derivative with respect to t of that whole thing. And the other side, 6 e to the t over 50. We can move forward with that. What do we need to do? Well, now, what we would like to do is we would like to move this dt over there. So then this is the differential of x e to the t over 50 equals 6 e to the t over 50 dt. Of course, we can integrate both sides. And integrating the left-hand side, the integral of the differential, just gives me back precisely that. The right-hand side, I get a 6. Integrating e to the t over 50. Of course, I could make the substitution and say I'll let u be t over 50. I wish it was just e to the t or e to the u. So if u is e to the, or u is t over 50, du dt is 1 over 50, meaning that dt is equal to 50 du. So that tells me that a 50 is going to show up here, replacing dt, and I'm going to have 50 e to the u du. 50 comes on outside. I have 300 e to the u. Du is just going to integrate as e to the u, so that's e to the t over 50. So now I have that. Of course, plus c. And now we can take this and say divide through by e to the t over 50. So we'll divide by e to the t over 50. We'll get x equals, we'll have 300 e to the t over 50 divides out there, plus c e to the minus t over 50. And now in order to figure out what c is, we have to know something else, okay? And at time equals 0, we know how much salt was in the tank. Right? At time equals 0, I said there's 50 gallons of salt in a 100-gallon tank. So at time equals 0, and t is 0, x of 0 is 50. And that equals 300 plus c times 1. E to the 0 is 1. And therefore c equals minus 250. And my total expression here, x t is then 300 minus 250 e to the minus t over 50. Now, what's going to happen? Well, eventually, as time goes to infinity, this whole thing is going to go to 0. We're going to have 300 pounds of salt in the tank, right? Because that term is going to disappear. We started with 50. At time 0, this term goes to 250. And we have 300 minus 250. So it starts at 50, and there's going to be a gradual and exponential increase in the amount of salt in the tank because of the fact that there's an exponential decrease in this term. We have some maximum that's going to reach. As long as we don't put in a higher concentration than that, it can't go higher than that. But we're going to, over time, reach that point where, as time goes to infinity, we're going to get all the way up to 300 pounds in the tank. But that's the concentration as a function of time.